lecture 22. Last time we started on structured data and we looked at essentially Cartesian products and their variants. So, it corresponded approximately to records and variant records. So, Cartesian products and disjoint unions. Today we will look at sequences. So, let me just briefly recapitulate what we will have to do while structuring data. As I said, one important thing is to find constructors to combine simpler pieces of data into compound units, and then find deconstructors which explode those a compound unit into its simpler components. Right. So, looking at sequences, the main constructor, actually we should look at it this way. Long ago, the mathematician and philosopher René Descartes said that after addition and multiplication, the most important human intellectual activity is equation solving. Okay, so, in fact, that is also how school curricula and so on are designed, but of course, equation solving also means finding inverses of additions and multiplications. So, you also have subtractions and divisions, but equation solving is really a most fundamental activity. So, after these 4 operations, you could think of equation solving as the 5th operation, which is part of any branch of mathematics, right. So, the main constructor is that of an equational definition, right. So, given some data domain D, I can define this equation in terms of the unknown S. So, S is the unknown, okay. And the question that you are asking is, what is the solution of S for such an equation, right. You might be asking actually what are the possible solutions of S which satisfy this equation, right. So, if you look at it that way, one solution, or what we might call the least solution, is that of D star. And what is D star? D star is defined as, let us say, the union. If you want, you can take this also to be the disjoint union, which I do not know how, maybe I could write it like this. So, in this case the disjoint union would work just as well. So, you can take this as this union of S n, where S 0 is the singleton set consisting of the empty sequence, and S k plus 1 is S Cartesian product S k, right. So, this solution to this equation is actually what might be called the least solution. It is in fact the smallest set S, which when you substitute on both sides for S would yield an equality, right. So, and since it is actually the construction of ordered pairs, right. You construct, so S k plus 1 is an ordered pair consisting of 2 elements. The first element is an element of D and the second element is an element of S k. I mean that is the way you should look at it. So, this is in fact the natural motivation why most of these functional languages actually provide some form of head and tail functions, because a sequence is really a Cartesian an ordered pair of whose second component might be another ordered pair, and so on and so forth, right. So, So, the deconstructors are just the head, tail, and maybe the I do not know. So, the constructor really is the cons operation, if you like, which comes from here. Otherwise, and the deconstructors are just the head and tail functions. Now, if you look upon it as just equation solving, then this is not the only solution. Okay. There are other solutions to this equation. For example, you could have infinite sequences also as solutions to this equation, right. So, if you consider d star plus d infinity, where d infinity is this collection of all infinite sequences. Okay. For the moment, let's look at it then this way, then this d star plus d infinity is also a solution to this equation, and it is in fact, this solution is in fact the largest solution to this equation, yeah, right. And as far as infinite sequences are concerned, a way of looking at, you could look at infinite sequences also as an infinite sequence could be regarded as an ordered pair whose first element is an element of D and whose second element is another infinite sequence. So, I mean, so the same head, tail and cons functions are equally applicable. So, the constructors and deconstructors that were used for this are equally applicable also for infinite sequences. Yeah, infinite sequences, though we will not be looking at them in some detail, are actually present in some form in ML. Okay, the lazy evaluation mechanism of ML actually has these infinite sequences. D is some domain, some data domain, something that you already know. S is the unknown variable.
What was the other last thing? S is equal to?
S is equal to D star.
No, equation. S is equal to in the curly, and this is not equal to.
Oh, this is the empty sequence.
Empty sequence.
This is the empty sequence. This is D cross S. Okay, where S, so a solution for this equation I said was D star, where I defined D star as the disjoint union of all. I am sorry, maybe I should have called this, maybe I should have used Dn. Yeah, I should have used Dn. So this should be Dn. Okay, where D naught is the empty sequence, dk plus 1 is D cross dk. Yeah, so I hope that clarifies the matter, right. So, oh, I used S throughout, though of course what I had written was also not wrong. Let me clarify that. Yeah, so that was also equally correct. So, for any solution, if you had done these operations, you would have got that also to be a solution of this equation. Okay. So, anyway, that's immaterial. The least solution, but however that is not the least solution. The least solution is that which is obtained by using D, right. And so, we could just as well, there are other solutions, for example, which could like infinite sequences. So, if you add infinite sequences also, then you get another solution which might be called the greatest solution. So, this equation really has only two solutions, right. There are really no other solutions, and so these are, you can loosely look upon them as this is something as a set definition. Normally you do not see a set definition which is recursive, okay, but in fact computer science is full of set definitions which are recursive. In the early Jurassic period of this course, we looked at context free grammars, right. So, if you take a context free grammar of this form, let us say Yeah. So, the question that you can ask is, what is the language generated by this grammar? Yeah. So, if you ask the question, what is the language generated by this grammar, you are also, you might equally well ask the question, what is the solution, what is the least solution to the equation given by this? Okay. So let me rewrite this properly. What is the least solution to this equation? That's what you are really asking. So that's why equation solving is absolutely basic. So where of course I have used a very loose notation. This 0 and 1, this S is presumably supposed to be a set, and this 0 and 1 I have used them around S to denote that every element of S is padded on the left with a 0 and on the right with a 1. Okay, I mean, so it's the normal prefixing or suffixing operation on strings. I have just generalized that to sets of strings, right. So you can ask this question, what is the least solution to this equation, and in fact that is the language generated by the grammar, right. So equation solving is really fundamental, is absolutely fundamental, and so almost all things that we talk about computationally are instances of equation solving. In fact, most of the equation solving that we do in computer science is of finding what might be called fixed points. Yeah. So all recursive definitions, any definition which is recursive, in particular this grammar is also a recursive definition. This set is defined in terms of itself, and so is a recursive definition. All recursive definitions are essentially equations which have to be solved. And what is the meaning of finding a solution to a recursive to an equation is to find a non-recursive definition which will satisfy the equation, right. So, and what does that mean? That means finding a fixed point. Everybody knows what a fixed point is? No. If you look at your standard methods like let f be a continuous differentiable function over this interval on the reals. So then f on the reals, you want to find a root, you want to find where this curve intersects the x axis. Okay. So what you often do is you are essentially solving the equation f of x equals 0. Okay. And in order to solve this equation f of x equals 0, which is finding the root of this function, what you often do is you manipulate things so that you get an equation of the form x equals g of x. And then way back in the 16th century somebody said that the solution to this equation is defined by the recurrence right. Okay. So this is so you can look upon this, the finding the root you somehow you do some transformation and get an equation of this form, which is very much like giving an recursive definition to x. Okay. So, I could look upon this as giving a recursive definition to x, and given a recursive definition to x, I give an iterative solution which is a recurrence. So, I can use recurrences in order to give iterative solutions to what might be called fixed point equations. Yeah, I mean this is standard on real numbers, there is absolutely no reason why one should not do it on sets, right. So, this solution that I am talking about, these solutions are in fact are also recurrences in that same form. In fact, what I have given, so if you look at it analogously, this solution, this is a recurrence which defines an iterative solution to this equation, to this fixed point equation, right. So, this is clearly an iterative solution, and most iterative solutions will give you solutions to fixed point equations. Yeah.
So the grammar that you were mentioning, s equals 0 1 or 0 s1. So the form that you put it in the next line, s equals 0 1 plus 0 s1. Now the grammar generated will be the solutions to this or the least solutions to this.
The language generated, when we are talking about the language generated, we are talking about the least solution that will satisfy this equation. The least solution that will satisfy this equation in the sense that we want the least solution which is closed under the operation of prefixing and suffixing of 0 and 1 respectively, right. So, what we are saying is what is the least set S such that 0 1 belongs to S, and 2 if x belongs to S, then 0 x 1 also belongs to S. So, there is a closure property that has to be satisfied. So, any solution which does not preserve that this containment problem, namely that 0 1 should belong to S, and for all x which belongs to S, if x for all x that belongs to S, 0 x 1 also should belong to S. This is an important closure given by this definition, and the least solution that you can think of are all the possible purely nested bracket matchings, if you like, of 0 1s, you know, it's this. So the solutions, the language generated by this grammar, if you go through an iterative solution, is just 0 raised to n, 1 raised to n, where n is greater than or equal to 1. This is the set S. It is the least solution because I am not, for example, permitting infinite sequences. Okay, if you permit infinite sequences, there is a possibility of getting a cardinality that is greater than LF naught. I mean, you are actually finding accumulation points of or limit points of sequences. I do not know whether you have done all these things, but it's a topology which is completed by something. Anyway, let us not worry about that. But the point is that there are okay, so this is the least solution, because the least solution in the sense that it has to satisfy these two closure properties. You take any set smaller than this, okay, I can find that there is an element in that set which does not satisfy one of these properties. Okay. So, we are usually talking always of least solutions, not necessarily always now, but we are always talking of least solutions which satisfy this such closure properties. So, if you were to take this constructor, for example such a domain equation, then no set smaller than d star will actually do for you. If you take any set smaller than d star, either by removing some elements or by just putting a bound, some bound n, then I can find a sequence which does not satisfy these closure properties. For example, I can take an n element sequence. Okay. For any n element sequence, it does not satisfy the property that if I take that n element sequence and an element of d as an ordered pair, then that ordered pair belongs to the set S, because it is an n plus 1 sequence. So, the smallest solution that you can get is just only the set of all finite sequences of elements of D. You can't get anything smaller than this, because there is a closure property to be satisfied, right. So, very much as Newton gave a solution to this fixed point equation, you can give solutions to such fixed point equations, and in fact most of our recursive definitions in computer science are really equations to be solved, and they are fixed point equations to be solved. And what is most surprising is, if you did a course on semantics of programming languages, you will see that in fact the way you obtain solutions to those fixed point equations is also very much like the way Newton did it for continuous differentiable functions. Okay, I mean, so there's very little. I mean, the analogy is absolutely striking, right? So you can have also infinite sequences as solutions to this equation, right? Where we might look upon, so you might just look upon an infinite sequence loosely, but then more particularly when we talk about an infinite sequence, or at least a sequence that is infinite on one side, not necessarily infinite on both sides. Okay. When you talk about a sequence that is infinite on one side, we can look upon that as a function from natural numbers to the domain. I mean, after all, when you consider a sequence, the most natural thing is to write a sequence as a1, a2, a3, a4, a5 and so on and so forth, which essentially means you are drawing a mapping from the natural numbers to elements of the domain. You are saying that the first element is a1 and the second element is a2 and so on and so forth, right. So this d infinity itself is a solution to this equation, and is in fact it is not the least solution, because the empty set is the least solution for this equation, but it is the least solution other than the empty set, right. So whenever you think of recursion, think of equation solving. Whenever you think of equation solving, think of equation solving by solving a fixed point equation, and when you think of a fixed point equation, solve it by a recurrence. I mean, find a suitable recurrence which will satisfy it, and that's that's the basic idea. So if you look at any sequence, so as I said, we could look upon infinite sequences as just each infinite sequence, I can regard it as just a structured data element containing an infinite number of components in some order, or I can look upon that merely as a function from the natural numbers to my data domain. Okay. So this function basically tells you what is the first element, what is the second element, what is the third element, and so on and so forth. So you can think of that infinite sequence, as a function defined by enumeration, yeah, by an infinite enumeration. So what we could also do is we could also think of other sequences as functions. So, even though we defined those sequences as ordered pairs, we defined a k plus 1 length sequence as an ordered pair consisting of an element of D and a k length sequence as a second component, right. However, we could just collapse all that and we can look upon every finite sequence as being isomorphic to a function defined by enumeration, right. So, every k length sequence you can look upon that either as just a k length sequence of data elements or as a function from the set 1 to k to the elements to D, right, where of course the empty sequence is the unique function from the empty set to D, right. The domain is empty, so so it does not matter really what the codomain is. I mean there is only one possible function from the empty set to any domain D. Okay. So, you can look upon the empty sequence as just such a function and you can look upon any k length sequence for k greater than 1 as a function from 1 to k to D, yeah, right. So, the set of all k length sequences is just the set of all such functions is isomorphic. I mean this is isomorphism, right. I mean all I am saying is that there is a one to one correspondence between the definition of Sk as we have given before and this set of functions, right. And this is the basic idea behind arrays.
How is it a function from 1 to k to D?
Yeah.
How is it from to D?
So let's take a k length sequence of integers. So I have this sequence 8 3 4 8 2 1. Okay. The first element, what is the first element? It is 8. Okay. So this is a function f of 1 is 8, f of 2 is 3, f of 4 is also 8 and f of 6. So, this is a 6 length sequence, f of 6 is 1. I mean, what has happened is that long years of writing functions in closed form have made you forget that you can actually write a function by enumeration. I mean, why not, right? I mean, you can look at the graph of the function, right. So, a sequence is really a function in that sense. It is a function not defined in this form f of x equals x square. This is a definition which is not by enumeration, it is a definition by a predicate, right, if you like. Okay, but you can also have functions defined. After all, the definition of a function just says that for each element in the domain there exists a unique element in the codomain, which means that all it means is that you can't have an arrow of this form. I mean you can't have two arrows from the same element of the domain, that is all. Otherwise, so you could write a function out by enumeration, that is as good a function as any other, right. So, so sequences could be regarded as functions. It is important to know that data and control is really functions. When we do the lambda calculus, you will see that there is really no essential difference between data and control, but then that you already know. In the case of your computer architecture course, both data and control are represented as data, right. I mean the fact that you got opcodes for every instruction, you are not really doing much control, you are just representing program as data. Okay. There is an alternate view in which we can look upon all data as functions and all control also as functions, and that is what we will study in the lambda calculus when we come to it. But in the meanwhile, the fact that finite sequences are, this set is isomorphic to the set of all functions from this closed interval 1k to D also gives us the reason why we might look upon arrays in programming languages as functions. So, arrays are really functions defined by enumeration. Yeah, it is important for us to look upon sequences in their generality, so that we understand that there is an underlying unified whole called the sequences. We should not be misled by the fact that arrays look different from files and lists and so on, but fundamentally they are all sequences. Okay. So, the only difference is that arrays are functions by enumeration and they are functions over a finite index set, yeah, of some component type. This is of type D. So, your very basic declaration in a Pascal like language is really that of a function specification, if you like. A is an array, something index set of type component, which is really specifying a domain and a codomain, and is specifying the name of the function to be A. Okay. It is a function defined by enumeration as opposed to a function defined by a closed form, and the deconstructor for such a function is just function application. So, how do you get a component out of the array? By applying the function, well, the function A to the component I, you get the ith component. It is as simple as that, right. So, this is the deconstructor, and just because there are reasons why you might want to look upon them as, but many languages, for example, do not distinguish between array component reference and function application at all. Okay, they use the standard parenthesis for array component reference, or subscripting if you like. So, the subscripting operation on arrays is really a function application. Yeah. So now, so if let us look at arrays, the one important reason why arrays are useful in programming is that they provide a form of direct access, what is known as random access. So if you look at the pragmatics of array allocation, what you would find is that firstly these arrays, especially since their bounds in a language like Pascal, their bounds are known at translation time. Okay. So, which means that you can fix the type of the component is also known at compile time, which means that you can give an accurate calculation of the space that is needed to store the entire array. Okay. So, if you can give an accurate calculation, then all your address calculations can be based on the stack and you do not need to go into the heap, right. So, which means that so the only thing that I require in my storage allocation is that I have to get to know, I have to be careful about one thing, and that is this index set, right. So, an array is a function from the index set to a component type. So, this index set is by definition an index set is any finite, an index set is any finite set, is any finite ordered set. So, it is ordered by, it is ordered either by a predicate, or more usually it is an index set. An index set is a finite set with the operations of successor and predecessor defined for all elements except the extremes. Okay. So that is also the reason why any enumeration type can be regarded as, you can take any enumeration type or a subrange type in Pascal and call that the index set of the array, right. So, the successor and predecessor functions are defined for all the basic data types except the reals. So, for example, a dense set, what is a dense set? A dense set in which is one in which between any two distinct elements there is guaranteed to be another element, right. So, any dense set is going to be infinite. So, dense sets cannot be index sets, okay. So, which means the logically the reals and the rationals are out. So, all you can have is some if you are talking of any finite set which is ordered by a successor and predecessor relation, then this index set is isomorphic to some set, some ordered set of natural numbers for some k, right. So, this index set, so in fact, so you can if you look at an array definition of this form, array let us say a to z of integer, then you are really you are looking at a function that is a composition between this isomorphism from index set to this set where k happens to be 26 and integers. This is an ordered finite ordered set with a successor and a predecessor defined on it. You can also have an array of for example, it has to be false, true, yeah, false is less than true. So, so you could have arrays of this form too. So, as long as a successor and predecessor function are defined on the index set and it is ordered in some way, the index set can be placed in one-to-one correspondence with the closed natural interval 1 to k for some k, and therefore, any array could be defined in terms of any such index set, right. So, in fact, these subrange types and these enumerated types in Pascal are actually implemented by this one-to-one correspondence, and since they are I mean what you do is you actually create a table with an order, you actually create, in fact what you do is you actually create an array and put the elements in that order, so that you have already performed the mapping by an enumeration mechanism, right. So, so we were looking at storage allocation. So, the only other problem that you have to worry about is really that of bounds, checking bounds at runtime, and for that you require what is known as a runtime descriptor. So, here I have given a picture of a single dimensional array. So, it's called a vector by Pratt, but anyway that is not it is not important. So, what you have is, in order to be able to perform runtime checks on indexes, you require to know the lower bound, the upper bound, and the type of the component and the amount of space each component is going to occupy. And you store, since you have to do runtime checks on expressions which are going to access components of the array, you require to store this descriptor along with the array on the stack as and when you enter a block which declares this array, right. So, the array is actually the data of the array is actually stored down here. So, this is how most of these languages which involve runtime checks on array bounds actually perform these bounds, because they keep a descriptor which is created, this descriptor template is created at compile time, and there is enough information in the declaration of the array to give you this to have this stored somewhere, and each time on entry into a block during execution time you first store this descriptor on the stack and then store the actual array elements after that. And so, you can do a direct address calculation which is which is quite trivial. Yeah. So, there is so if you look at array access whether for L value or R value, you still have to get to the component, get to the location of the address of I. So, then there is a base address which of course is runtime, which is not compile time determinable. So, relative to this base address, there is a descriptor size which is compile time determinable. There is of course an I, this I need not be an index, it might be an expression on the data type of the index set, and therefore, this I is not compile time determinable. However, the lower bound and the size of the elements are compile time determinable. So, which means that you have to do a certain amount of compile time computation as part of your array creation mechanism, and the rest can be a runtime computation. Okay. So, the actual direct access and the meaning of direct access, or it is more wrongly called and more often called random access. It is not, it is what you mean is direct access, and the direct access means that the direct access does not have to go through the structure in sequence to find an appropriate element, but that you can do an address computation outside that structure and hit upon the absolute address of that component directly. Yeah. So, and that of course involves this very trivial runtime computation. Yeah. So, however, what happens is that most languages, most machine architectures usually specify some byte length or some word length. Very many architectures starting from the IBM 360 actually specified that all integers should be in half word boundaries, all floating points should only be in full word boundaries, where a word consisted of 4 bytes. Some machines like the DEC system 10 had a word consisting of 5 bytes, and then they had all these complicated things like you can store data only starting from a word address or a half word address or some such thing. So, and so the whole point was that the underlying assembly language provided operations which worked fastest on word boundaries or half word boundaries, and worked much slower when you had to pull apart the individual bits of a byte one at a time. Okay. They could do these parallel Boolean operations on words, they could do parallel Boolean operations on half words, but sequentializing all those operations bit by bit would slow down the machine extremely. So, they always recommended that you stored data in such a way that they occupied word boundaries, so that they might exploit the parallel Boolean operations to the fullest extent to give you the maximum throughput, right. So, what happens is that as a result, when you take this when you store arrays, you will be storing them mostly according to some architecture specified boundaries, so that the computations are fastest. However, if storage is at a premium, then what you might want to do is you might want to use a packed representation, right. So, then if you are going to use a packed representation, what it means is that you are disregarding, the storage is more important to you than actual computation time, and so you are disregarding all those all the advice that the architect of the machine gave you regarding fast operations. It is more important for you to be able to pack as much data as possible into a single word rather than to do faster computations, okay, maybe because you got tremendous amount of data. So, then when you have packed representation, then what you are usually doing is you are not going to stick to the discipline of word boundaries or byte boundaries or half word boundaries. What you are going to do is you are going to move things to occupy as small a place as possible, which means that a certain data item, for example, if you have integers only from 1 to 100, then it is not necessary to store an entire to allocate one word to each integer. You could allocate one word to 4 integers. If it's so if you have just if your integers are all going to be less than 2 raised to 8, let us say or 2 raised to or 2 raised to 4 or some such thing, then you are going to pack as many integers into one word as possible. And if you are going to pack that many, then what it means is that you cannot exploit the parallel application of those logical operations that the machine architecture provides you, which means in order to do them fast you have to unpack these integers and store them afresh in some place, do the computation and store them back in this packed fashion, right. So, so one thing is that, so any kind of packing mechanism means that your access to individual components will no longer be direct, and secondly, if you want faster computation you will have to unpack that representation. So, you might use more intermediate storage in order to gain faster computation, but you are going to lose some time because of unpacking and packing again, right, because that is an extra loading and storing. Packing and unpacking and packing also means accessing individual components which whose addresses are not integral multiples of whatever is the basic unit in the machine memory, right. So, packed representations are likely to be slower and more expensive and are going to be used only when the data is so huge and it is possible to save on storage space. If storage space is at a premium, it is possible to save on storage space, but you do not but at the expense of slower access and slower computations, right. So, this notion of arrays can be easily generalized to multidimensional arrays. All it means is that your runtime descriptor should also include information about the dimensions, and the dimension for each dimension of course you have a lower bound and an upper bound specification. So, you have to specify them in a particular order, which is also going to be reflected in the representation of the entire array. For example, a 2-dimensional array could be represented either in row major order or column major order. By row major order, what do I mean? I just mean this. I think you must have all studied that in data structures, but so if you have a matrix of this form A11 to ANN, a 2-dimensional matrix is going to be represented linearly in memory. If it is represented in row major order, then you are going to have A11 to A1n followed by A21 to A2n and so on up to ANN. So, this is row major, that means the matrix is regarded as a vector of columns, as a vector of rows, as an array of rows if you like. The other alternative is a column major order, which means that you would A11, A21 and so on up to AN1, and then A12 and then so on up to AN2 and so on up to ANN. This is many of the initial Fortran and even now many Fortran compilers actually use this column major ordering. That means they represent the 2-dimensional matrix as a vector of columns, whereas most languages nowadays, Pascal and so on and Ada, would represent a 2-dimensional array in row major order, which means they would represent a matrix as a vector of rows. Yeah. So, the generalized, so in the case of multi dimensions, again you can write an easy formula to do a direct access calculation of the address and separate it out into translation time computable component term and runtime determinable term. The other kinds of sequences that we might have in that we use are strings. So, normally the strings are stored in heap. Sometimes the heap is divided into a separate string space where all strings are stored in order to gain access are stored contiguously with just a single descriptor which gives the length of the string, and the most and they are very often stored contiguously, because each character in a string does not require more than 7 bits. So, you could afford to store them in an 8 byte word contiguously, for example, or of course, you actually use the heap for dynamic data structures and you use it as part of the dynamic data structuring, which is but this means pointer traversal and it can make things slow. So, a language like Snowball 4, which is meant specifically for string processing, would try to store all the strings contiguously without having to use pointers, right, without having to use too many pointers. There are languages like PL1 which allow fixed size strings. So, which means they could be stored in the stack because their length is calculatable, or fixed bound, but variable size strings, which means you specified an upper bound on the length of the strings, but you are not you do not guarantee to use all of it. So, which means your the runtime descriptor for that kind of a string would contain both the upper bound and the current length of the string, so that you know exactly how much you are using and you are not reading more and more garbage that is there at the end of that allocated amount. So, then in such cases these strings could be stored directly on the runtime stack, since their sizes are compile time determinable. Lastly, you have files. This thing that looks like an idli pan to make idlis in a pressure cooker is actually the disk drive or some secondary storage device. So, in the case of files, there is a logical difference between the program read and write operations and the actual transfer to and from the secondary storage, which is this idli pan. Yeah. So, usually the transfer is by a block, and there is a file information table which is stored, which usually contains various information. Firstly, what area of the disk did this piece come from, or what area should it go to. Secondly, it should also the actual read and write from the programs, I mean there should be a pointer to the actual area in the buffer where the current pointer is, right. And so, very often the actual transfer of data takes place at an idle time for the processor, or it is just handled directly by the IO processors, which means you have to have interaction with the operating system on which you are implementing your language. Yeah, there is and these are only sequential files. Languages like COBOL allow direct access and index sequential access files, which means that essentially the structure of directories has to be pulled down into data components within the file, and you will have to store addresses, disk addresses, cylinder sector addresses in some files, so that you can do a direct access onto the disk for the block of storage which contains the data you are looking for. But then that means a lot more intensive computation. Lists, well, there is nothing to say about lists. So, they are just stored in the heap, right, and they might either be controlled, they are usually programmer controlled, they are automatic in functional languages, and the allocation and deallocation depends upon whether what kind of a list it is going to be. Yeah, so next time we will start on control structures.